All right, let's see. Should I hold this? I'm going to leave it. Okay, so thank you, Lindley. So about 2 years ago, we were assembled in Tucson, and it was a program review for the NEO program office, and we're talking about what everybody was doing, and we had some talk about doing some exercises, and I love tabletop exercises. We have one going on right now. But the other half of my life is working with the Air Force, like how Lindley used to do. And they try to do things more in the real world. So I told Lindley, I said, like, why don't we do something for real? I like tabletop exercises, but we should do something real. And Lance was there, and he came up with this target, 2012 TC4, and said it's going to make a close flyby of the Earth, and we should go and try and observe it to try and use it as a planetary defense target. And I told Lindley, let's do this. And he looked around, who's going to lead it? And I was the one holding the mic, just like now. So I ended up, being responsible for corralling everybody together to make this exercise happen. So the goal statement we came up with was to, the asteroid 2012 TC4 is going to make a close approach of the Earth on October 12, 2017. At that time, based on its previous observations from its previous opposition, it was going to fly by at a very close distance. It was 6,800 kilometers or so from the surface of the Earth. So it was really interesting target. It was a 20-meter object. And so the goal was to recover, track, and characterize TC4 as a potential impactor. So Davide did the magic on the orbital parameters to nudge it enough so that we could use it in the impact modeling case for TC4, so that we can try and exercise the entire planetary defense system. So from observations, modeling, prediction, and communication. So we actually had the entire planetary defense alert system going through the chain of command at NASA and also at the White House, but of course we had a lot of information that said exercise, 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 just in case the person, who can push the button does not do it. So the goal is doing impact risk modeling. What we want to do is collect the measurements that are going to go into this impact risk model. So you have things like H magnitude that comes from the Minor Planet Center, the albedo, the object's trajectory, the composition of the object, and try and use these measurements to derive some parameters. For example, the diameter, density, strength, the velocity, and the entry angle, and things like that. So the goal was to collect these observations using different techniques and feed them to Jessie Dodson's group at NASA Ames, and she would run different scenarios at different times of the campaign. When you first start doing astrometry, you really don't have much information about its size. So when you have an H magnitude and associated uncertainty in the diameter based on the H magnitude and assumed albedo, you have poorly constrained impact scenarios. So how our impact modeling prediction, the risk prediction, changes as new information comes in. That's one of the things we wanted to find out. And we also dealt with media. So here's the animation of the original trajectory as we thought it would happen. TC4 is this. You're riding behind TC4. Here's the geostationary ring, and of course, it makes a really close pass based on its previous orbit, the information we had about it. And that's the ground track. And so here's another one. The object starts up here, so you get an idea. So it was really exciting when we first saw this as a possibility. So you see why we picked the target itself for doing this mission. So we put together a coalition of the willing. We decided not to force anybody into this, but a lot of people stepped up and said, like, okay, finally, we're doing something for real. So we had about more than 100 people, from observers, from media people, of course, a lot of people at NASA headquarters itself. We had 30 observational assets spread around the world, just to give you a little perspective on things. In the end, I think we had about 14 countries participate. Of course, the Weiss Observatory in Israel, Goldstone radar, the KMT-net telescope in South Africa, the Russian 6-meter, and of course the VLT, which is very important. We organized the whole campaign on different techniques or different aspects of it. So we had astrometry led by Davide. I know where Davide is. So he's there. Oh, there you go. So, and then photometry was led by Bill Ryan from Magdalena Ridge. Christina Thomas at NAU. I think Christina is in the audience as well. Led the spectroscopy effort. Lance Benner from JPL, you heard from Lance before lunch, led the radar effort. Impact risk modeling was done by Jessie Dotson and her group at Ames. The media was handled through NASA headquarters by Laurie Cantillo at that time. She's now at JPL. And of course, IWAN was led by Rob Landis. The way it worked out is that we didn't quite exercise IWAN as such. We just went with the flow to see who all we can get as part of the coalition of the willing. So, but we're trying to do something different soon. So the recovery, you've seen this picture of movies before. Marco Michelli and their group first recovered the object using VLT. It's the faintest asteroid ever recovered with the telescope from the, I think, from the Earth or from space, I guess. To give you an idea, I think it was at magnitude 27. It was about 60 billion times fainter than the faintest star you can see with the naked eye. So it's right there. And soon after we got about 700 observations throughout the 2017 campaign. And we realized that once we had a new orbit, Davide was constantly updating the orbit. The flyby distance was going to be a pretty safe 50,000 kilometers, not as the 7,000 kilometers we originally thought, based on the previous orbits itself. The rotation period is the work done by Bill Ryan and their group. So you can see TC4 itself, right there. You can see it blinking. It was rotating once every 12 minutes or so. And so this effort was led by Bill Ryan. It also was a non-principal axis rotator, so that information was useful. And then, of course, radar. So since this object was making a close flyby, you had to do bistatic because you had to switch between transmitting and receiving it. So we were going to transmit out of Arecibo and receive at Green Bank. In a real life scenario, things happen. So for example, Hurricane Maria had a pass with the island of Puerto Rico and took out the Arecibo radar. So we had to come up with a contingency where we could transmit from Goldstone and receive at Green Bank. So here's the trajectory of the object. The blue lines you see going by are the radar observations before and after the flyby itself. And here's the actual object. Remember, this object is very small. So you see a small movie. So the effective diameter is about 10 meters across. Initially, before the flyby, we thought it was a 20-meter object, about the size of Chelyabinsk. This basically made us realize that it's a very bright object, optically bright object, because it had a smaller diameter compared to what it was predicted to be based on the H magnitude and assumed albedo. Spectroscopy. So I was teaching a class at that time, so I thought it was a great idea to take all the students in the class up to Mauna Kea. So we raised some funds with our department external board, and I managed to get about a dozen grad students up to observe at the IRTF to try and constrain its composition. It mostly went fine. A couple of kids got sick, but the interesting part is that we tried to observe one night, and it was bad weather, but we were doing it from Hilo, and then we got up to the mountain after 2 days to actually do the observation. Perfect night. Everything was clear. I had my A team on the console, ready to work. And then what happens? The power goes out. Okay. Then the kids looked at me and it's like, it's all part of the exercise. Just go with it. It's like, So then an hour and a half goes by and then the power comes back on. But then the telescope operator could not find the breaker switch. So we spent about 4 hours trying to figure it out, So we managed to get some information from the observations we had taken a couple of days ago, but on the best night possible, I thought Lindley had turned off the power deliberately to make it really real. So as I said, there was a really bright object. So its surface is very similar to a meteorite type called Avrites. The spectra that we got and also the radar circular polarization ratio suggests that it could be similar to an X or a E-type object. And so this basically reflects about 50% of the light. So it's a very bright object, and the 10-meter diameter goes with that. The lessons we learned is that, given the time scale, we had, and also, what big of a mess that I thought we had inherited, it was really literally herding cats, right? It was really challenging. I thought it was very successful for what we did. The astrometry, photometry, and the impact risk modeling and the media aspect especially worked without any major issues. And of course, we had to have contingency plans for natural disasters, like such as hurricanes for the radar itself. The one thing we learned is that when you do astrometry, you have an urgency to submit it because the data you collect has a expiration value. Once they update the orbit, you can't sit for a week or 2 weeks or 3 weeks, and then send your astrometry. And it'll still be useful, but other data sets would supersede. But it's not quite the case with characterization, and me being a characterization, but I'm guilty of it too. So we'd like to sit and marinate on our data. So in a planetary defense scenario, when you have operational needs that need to be met, can you sit and mill around and mess with your data as long as you want or not, right? So I think going forward, it would be a good thing to exercise the characterization part so we can figure out a timeline as like how quickly can we get a rotation period? How quickly can we get composition? How quickly can we get a diameter? So that's something. And the interesting part is that I went down and tried to find out what happened with the power cut, because I want to know what caused it, right? So I made some phone calls, and the best story I got was that there was a gentleman that was trying to trim a tree late in the evening, and he had accidentally, put it in such a way that it had hit the power line and taken out the power for the entire mountain on the day of the TC4 campaign. So, basically that's the last lesson. It's like, never trust a person with an axe in the dark. So we are implementing several changes. So obviously we have a contingency now for IRTF for power backup. So I also chair the management operation working group for the IRTF and KEC. So we implemented that. But we are going to focus something on characterization. This is called the 1999 KW4 campaign. This is coming up very quickly. So KW4 object would fly by the Earth on May 25th. So it's less than a month from now. It's primarily focused on characterization. There's no astrometry part of it. It's photometry, direct imaging, radar, spectroscopy, and also we're trying to observe it with the Hubble for direct imaging. So the characterization word is the key here. And it's also led from a different perspective. We're trying to see how it would be done in a real life situation where I1 would be the one leading and contacting observatories and doing. So Rob Landis at NASA Johnson right now is leading the I1 effort because he's the I1 point of contact for PDC. But if there's anybody here who wants to join this effort, we have the same team back almost. I think Jesse, we can't replace you, so Jesse's there. I'm doing the characterization part. I think Patrick Taylor is doing the radar. Photometry is done by Peter Pravec, and direct imaging, I think Olivier is doing it. So anyway, if you want to join, email me, and with that, I'll take questions. Thank you. Lance.
Hey, Vishnu, I just want to correct a minor misperception. Goldstone was not the backup plan.
Okay.
We were the primary plan.
Okay.
Because we were able to observe it when it was at southern declinations before the encounter that Arecibo was unable to reach. Sure. And we also have the ability to image it at 2-meter resolution, which is 4 times finer than is possible at Arecibo. The Arecibo observations would have been invaluable if they could have happened, because they could have tracked it much longer than we could, but Goldstone was always the primary plan.
Sure. Thank you.